You know, every year, the Nobel Prize in Chemistry honors a discovery that totally reshapes our world. And recently, the prize went to something that gives us a brand new way to build matter itself. We're talking about a revolutionary class of materials called metal organic frameworks, or MOFs. Just think of them as programmable molecular sponges. And what they can do is, well, staggering.
Okay, but what does that actually mean in the real world? Let's start with a crazy question. What if you could build a material so precisely designed that it could literally pull fresh drinking water right out of the thinnest desert air? I know, it sounds like something straight out of sci-fi, but that's the kind of power we're talking about here.
And believe me, that is just the tip of the iceberg. This same basic technology can be programmed to do so much more. You can tweak it to capture CO2 right from a smokestack, or you can design it to filter out those awful forever chemicals from our water. It can even store something as tricky as hydrogen fuel safely and efficiently. I mean, we're talking about a single platform that can tackle some of humanity's absolute biggest challenges.
All right, Section 1, Chemistry's 3D Wasteland. So to really get why this is such a huge deal, we got to rewind the clock a bit. For most of history, chemists have been absolute masters at making individual molecules. You could call them zero-dimensional things. But building these big, sprawling, porous, three-dimensional frameworks? Whoa, that was a completely different ballgame.
And you don't have to take my word for it. Nobel laureate Roald Hoffmann, he put it perfectly. He called the challenge of building in 3D a synthetic wasteland. This wasn't just, hard. For a long time, the best chemists in the world thought it was basically impossible to do with any kind of predictability.
See, making a single molecule, that was a controlled, predictable process. You follow the recipe, you get the result. But trying to build a stable, porous 3D solid, that was mostly just trial and error. You'd mix your ingredients, cross your fingers, and hope for the best. But more often than not, you just end up with a useless, collapsed mess.
Okay, on to our next part, the first unstable blueprint. So then, in the late 1980s, one chemist decided to take on this so-called wasteland. His name was Richard Robson, and he had a vision for a totally new way to build.
So in 1989, Robson has this amazing breakthrough. He combines copper ions with this specific four-armed organic molecule, and boom, he creates this incredibly ordered crystal. The best way to picture it is like a diamond, right? A perfect lattice of carbon atoms, but Robson's structure was different. It was like a diamond framework that had these enormous empty rooms built right inside. He had essentially created the blueprint for a molecular sponge.
But, and you knew there was a but coming, there was a huge catch. The structure was brilliant, but it was also incredibly fragile. The second you try to remove the solvent molecules that were filling up those cavities, the whole thing just collapsed in on itself. So it was this beautiful idea that just wasn't practical. Yet. All right, next section, building a stable framework. So the billion-dollar question was, how do you make this incredible structure strong enough to actually be useful? Well, that question would be answered by our next two Nobel laureates, Susumu Kitagawa and Omar Yagi. And, interestingly, they were working independently, but they would solve this stability problem once and for all. So, in 1997, Susumu Kitagawa gives us the first major piece of the puzzle. He proves that you could build frameworks that were not only stable, but could also act like these tiny molecular channels. He showed that gases like methane could actually flow into the structure, get stored, and then flow back out, all without the framework falling apart. This was huge.
And then, just 2 years later in 1999, Omar Yagi delivers the knockout punch. He creates this thing, MOF5, and it was just iconic. It was ridiculously stable, super porous, and had this massive internal surface area. MOF5 wasn't just another small step forward. This was the proof of concept that launched a global revolution in material science. Seriously.
And Yagi didn't stop there. He didn't just build it, he basically gave the entire field its operating manual. He called it reticular chemistry. And this was the huge conceptual leap that turned this whole thing from a trial-and-error art form into a predictable science. It meant you could now pick your molecular building blocks, kind of like Legos, and know exactly how to assemble them into a pre-planned structure. Game changer.
Part 4. The MOF Revolution.
So with this newfound power to design and build materials from the atom up, the floodgates just opened. That theoretical promise we talked about at the very beginning of this, it started becoming a reality fast.
So just how powerful are these molecular sponges? Okay, brace yourself for this. A single gram of a MOF called Nu-11, that's about what you could fit in a teaspoon, has an internal surface area of over 7,000 square meters. Let me put that in perspective for you. That is literally the size of a football field, packed into a teaspoon. That incredible capacity is what makes them so unbelievably powerful.
So what does all that power look like in the real world? Well, let's take a look. This one is CALF-20. It's been designed with pores that are the perfect size and have the perfect chemical environment to selectively snatch CO2 molecules right out of the air. This makes it a super efficient tool for carbon capture, especially at an industrial scale.
And hey, remember that whole water from desert air thing? Well, meet MOF 303. Its structure is programmed to have an incredibly strong attraction to water molecules. It allows it to efficiently pull H2O directly out of the air, even in really dry, low humidity places. Harvesting water from the desert? Yeah, it's a reality now.
And then there's this one, UIO-67, which is a total lifesaver. It's being used to specifically target and trap those harmful PFAS chemicals, the toxic forever chemicals, and clean them out of our drinking water. It's this ability to customize the pore for one specific molecule that makes this whole technology so revolutionary.
And honestly, the list of applications just keeps growing and growing. We're talking everything from hydrogen storage and speeding up chemical reactions, all the way to advanced batteries and even targeted drug delivery. MOFs are providing a completely new toolbox for scientists and engineers across dozens and dozens of fields.
Okay, last section, a prize for custom materials. So, why is this Nobel Prize such a big deal? Why does it change everything? Well, it's not just for discovering one single amazing material. It's for creating a whole new way of thinking about materials.
I mean, look at this journey. It goes from Robson's unstable blueprint back in 1989 all the way to the science of reticular chemistry in the early 2000s. And that journey, it fundamentally changed what's possible. It took us from just stumbling around in the dark to being able to design materials with atomic precision.
The Nobel Committee themselves said it best. They said this work has opened up previously unforeseen opportunities for custom-made materials. Think about that. We are no longer just limited to the materials we find lying around in nature. We can now design and build the exact material we need to solve a specific problem.
And that leaves us with one last really exciting thought. For the first time in history, we have the tools to design and build matter with almost complete control. The only question left is, what massive global challenge are we going to solve next?